In this talk, I will introduce Blockaid, a system for data access policy enforcement for web applications. Web applications are everywhere. These include social networks like Facebook and Reddit, and instructional software like Piazza and Canvas. What's common about these web applications is that they store and serve sensitive user information. For example, on a social network, Alice might send Bob a private message whose contents should be visible only to the participants, Alice and Bob, but not to anyone else, like Charlie. And so an important concern is to make sure that sensitive information be disclosed only to parties that should have access to it. We assume that the matter of what information can be accessed by which users is encoded in a data access policy, which in this example might say that a direct message should be accessible only to its participants, and so on. Today's web developers enforce these policies by manually inserting access checks in their code. These checks often take the form of if statements that ensure a user has sufficient permission before revealing a piece of content to the user. Unfortunately, these access checks are hard to get right, and missing or incorrect access checks have led to inadvertent data leaks in many production software, like the Piazza Forum or the Hotcrop conference management system. So the question we ask is, how can we systematically ensure that an application reveals only information allowed by its policy? To answer this question, we built Blockaid, a runtime data access policy enforcer for web applications. In the rest of the talk, I will first give an overview of Blockaid and its goals, followed by how policies are specified in Blockaid, how they are enforced, and finally, evaluation. Let us begin with an overview. As I mentioned earlier, Blockaid targets web applications. In our setup, we have a web application running on a server backed by a SQL database. We assume that all sensitive information is stored in the database, and that there exists a data access policy that specifies what data each user is allowed to access. Blockaid is a SQL proxy that intercepts every query issued by the application and attempts to verify that it reveals no more information than the policy allows. If that's the case, Blockaid lets the query through unmodified and then relays the results back to the application. But if not, Blockaid would block the query. As we can see, the overall goal of Blockaid is to ensure that the application reveals only information that the policy allows the user to access. Under this overall goal, we have 4 sub-goals for Blockaid. First, we want Blockaid to support a wide variety of expressive policies found in today's applications. Second, we want Blockaid to be applicable to applications written in existing popular web frameworks, like Django or Ruby on Rails. Third, we want Blockaid to be semantically transparent. What we mean by that is, as long as the application discloses information in compliance with the policy, we want Blockaid to keep the application's behavior unchanged. However, when the application violates the policy, we want Blockaid to raise an error visibly, rather than, say, silently changing query results to omit sensitive information fetched. Finally, we want Blockaid to incur low performance overhead. As far as we know, no prior system satisfies all 4 of these goals. And in the interest of time, I will focus on 2 of them, compatibility and semantic transparency, and briefly discuss how no prior work satisfies both of these goals simultaneously. There are 2 popular approaches to data access enforcement for web applications. On one side, we have query modification, which entails dynamically altering our query results to remove any sensitive data that might have been fetched. Many of these systems are compatible with existing web frameworks. However, this approach is not semantically transparent because it relies on altering query semantics at runtime, which could lead to queries returning unexpected results to the application. On the other side, we have static verification, which entails statically analyzing the source code of an application to make sure that it will never issue any query that violates the policy at runtime. This approach satisfies semantic transparency, because once verified, an application will run as is at runtime. However, it is not compatible with existing frameworks because this approach typically requires programs to be written in specialized languages, like Liquid Haskell, to facilitate verification. Blockaid satisfies all 4 of these goals. Let's take a closer look at how it works. Blockaid takes as input a data access policy, and at the beginning of a web request, receives a request context from the application indicating the current user's identity. It also maintains a trace of prior queries issued in the current web request and their responses to be used as context when checking. When the application issues a query, the query first hits the decision cache, which checks whether a prior similar query has been deemed compliant. If so, then Blockaid immediately knows that the current query is also compliant. If not, the query gets sent to SMP solvers, which will check compliance for us. Depending on the outcome, Blockaid either blocks the query or forwards it to the database unmodified and returns the result. In the latter case, the trace is also updated with the current query and its response. Now let's go into more details on these components, starting with how is the policy specified. In Blockaid, we specify a data access policy using database view definitions, which are simply SQL select statements that define what data is accessible to a user. As an example, let's look at how it might specify a policy for a simple calendar application, which has 3 database tables: users, events, and attendance. This policy has 3 views. The first view, select star from users, says that each user can view the information on all users in the system. The second view, select event ID from attendance, where UID equals myUID, where myUID is a parameter from the request context. And it says that each user can view the IDs of the events they attend. And finally, we have a third view, which joins the events and attendance tables, and it says that each user can view the details of the events they attend. Now, given a policy consisting of views, how does Blockaid enforce it? To answer this question, let me first explain what it means for a query to be compliant to a policy. So a compliant query is one that reveals only information exposed by the views, but nothing outside of it. So returning to our example, suppose a user with user ID 1 requests details on event number 2. To handle this request, the application first queries whether the current user is an attendee of the event or not. This query is allowed by Blockaid because the information it reviews is covered by view number 2. And so it gets sent to the database, and let's assume that the database returns 1 row, indicating that the current user is an attendee of the event. Then the application fetches the details on the event itself. The second query is also allowed by Blockaid because the information it reveals is guaranteed to be covered by view 3 on the left here, given the previous query and its result. In other words, the second query can only be allowed because the application has ascertained beforehand that the user is an attendee of the event. Now let's extrapolate from this example and define query compliance formally. Given a set of views, which indicate the accessible information for the request context, and the trace of prior query output pairs, we say that the query is compliant if for every pair of databases, D and D prime, that are consistent with the observed trace and contain the same accessible information, the query must return the same result on both databases. This property ensures that on the current database that the web application is interacting with, the query queue reveals no more information than is exposed by the views. So how does Blockaid check compliance according to this definition? To check compliance, Blockaid first turns the definition into a logical formula. The key to this step is to turn SQL queries into formulas in first-order logic. Blockaid does so by invoking Caude's theorem, which corresponds first-order logic to a simple subset of SQL, and by using several approximations to support more complex queries found in practice. The formula then gets sent to SMT solvers, which tell us whether the query is compliant or not. Or it might return unknown, in which case Blockaid has to conservatively block the query, although in our evaluation, no compliant query has been falsely rejected. Now, this approach works, but has a practical issue. That is, the SMT solvers can be really slow, taking hundreds of milliseconds per query. And this overhead can easily add up to seconds per page load, which is unacceptable. So to make compliance checking faster, Blockaid uses the decision cache, which, as I mentioned earlier, records queries that have been checked previously so that they don't have to be checked again in the future. Blockaid caches only compliant queries because they are the most performance sensitive. We expect non-compliant queries to be rare in production, as they typically indicate bugs and should be eliminated during testing. So how does caching work in Blockaid? Assuming a fixed database schema and policy, observe that compliance is simply a function of the triple request context, query, and trace. And so as a naive solution, what if we, after every time such a triple has been deemed compliant, we just store the triple in the cache so that a future occurrence of the exact same triple does not have to be checked again? This approach has an issue, because now every single cache entry is now specific to the user and the URLs visited. Because a web application have many, many different users and URLs, it is very unlikely that the exact same triple will be encountered in the near future. And so this naive caching strategy will have low cache hit rate. To solve this problem, Blockaid uses generalization. What I mean by that is, every time a triple has been deemed compliant, Blockaid generalizes it into a decision template and caches that instead. This decision template captures the core reason for compliance, and it will apply to any triple that contains the same structure as the current one, allowing Blockaid to declare them compliant without having to call the solvers again. And so this is how Blockaid can store a small number of templates and have them apply to an unbounded number of triples that can be encountered. So how are these templates generated? The key is to find a small set of constraints on the triple of request context, query, and trace that is sufficient to guarantee compliance. Blockaid does so by generating candidate sets of constraints and asking the solver whether each set is sufficient to guarantee compliance. The solver either returns yes or no, and in the yes case, also returns an unsat core, which is typically a subset of the constraints that the solver actually used to prove compliance. Guided by the solver output, Blockaid generates the next set of constraints to consider, and this enumeration continues until a desired set is found eventually. Please see the paper on more details on this generalization procedure. Let me end this talk with an evaluation. We implemented Blockaid as a JDBC driver wrapping a database connection, and our prototype can be used on any application that runs on the JVM. We applied our prototype to 3 applications for which we handcrafted policies. The applications are Diaspora, a social network, Spree, an e-commerce site, and Autolab, a course management system. We measured the page load time of a benchmark of 5 URLs per application using a client that resides on the same machine as the server in order to reduce performance variability. To make this benchmark work on the Blockaid, we had to modify roughly 20 to 100 lines of code per application. Much of this modification was mundane, except for one subtle case. For you see, these applications often fetch a lot of potentially sensitive data, but they're actually careful with not revealing this data to the user. So there might not actually be data leakage in this case, but Blockaid might block the queries in this scenario, because as a SQL proxy, Blockaid applies policies to what data is fetched by the queries, not what data is returned to the user. And so it was necessary for us to modify the applications to fetch only data that can be revealed to the user. Let's look at the performance. On the x-axis, we have the 15 total URLs in the benchmark, and the y-axis, the median page load time. Let's first look at the performance without Blockaid. At the baseline, the page load time ranges from 20 to 450 milliseconds. The modifications we introduced incur up to 6% overhead for all but one page, whose overhead is still under 5 milliseconds. Now let's run at the application under Blockaid. If all compliance decisions are cached, Blockaid incurs a modest 12% overhead over the modified application. But if we disable the compliance the decision caching, the overhead shoots up to over 200x over modified application. This shows that intelligent caching is instrumental to keeping the overhead low. Please see the paper for more evaluation, including a breakdown of the page load times, the solver performance, and the case study on template generalization. In conclusion, Blockaid is a data access policy enforcement system for web applications. It demonstrates that it is possible to build such a system that is compatible with existing frameworks and semantically transparent. Blockaid achieves this by using SMP solving to verify query compliance with build-based policies. And the key to getting good performance was a generalization-based caching technique through decision templates, a technique which we believe can also be applied to other solver-aided applications as well. Blockaid is open source. You can find the source code and artifacts at this URL. Thank you, and I'm happy to take questions.